Hi, good morning one and all. This is again Dr. C.H. Kiran Kumar dealing you the machine learning part. So today we will see what are called the next topic of tree models. Tree models, my dear friends. Unit 3, chapter number 5. Now, till yesterday we have seen how to calculate entropy, gene index, how to select an attribute as a branch and all. Now we will see what are the effects. What are the effects? Ranking. We have to see now ranking, my dear friends. Ranking. We all have seen all these things. Now, let us see. Now, suppose we have finally made a decision tree. Now, this is called A, my dear friends. This is A. This A, no, if we draw a graph about all this A, B, if A, B, C, D, E, F, G, H. So suppose if we draw if we plot a graph, it looks like this. A cuts. A is just a true or false, my dear friends. So everything comes. So we have divided all negatives and positives. So negatives are one side and positives are the other side. So all negatives are one side and positives are the other side. And our RUC or AUC, area and curve is this. This is our area under curve. Now, after that, we have split it. Now, we split B. B. How did we split C? Let us see that. B. This is called B, my dear friends. This is B. This is B. This is B. B మూడు సార్లు కట్ అవుతుంది. This is the place first cut. This is the second cut. And this is the third cut. Hope you understood. So B, the B curve is this area. The B curve is this area. B curve. Hope you understood, right? Similarly, for instance, the root of the tree covers all positives and all negatives, and hence represented by the ascending diagonal A. Once we add our first split, segment A is replaced by segment B. This is what segment B is. Is replaced by segment C, B and C, B and C, B and C. Segment B and segment C, B and C. Segment B is further split into D, D, this is D, F and E, D, E, F, D, F, E or D, F, E. Finally, E split into two pure nodes, H and G. Pure means no negatives. There are no negatives here, no negatives. This is called curve or curve graph, whatever it is. So this is called coverage space, my dear friend. Coverage space. But the problem is, here the problem comes. The problem is, see, the ranking obtained from the empirical probabilities in the leaves of a decision tree yields a convex ROC curve on the training data. See, in the above example, if you see DFHGC, DFHGC, DFHGC forms shows the AUC, area under curve, which covers all positives and negatives. But See, you can definitely say that D, F, H, G, C covers the entire positives and negatives. But so this D covers entire positives. F, we can't say that. D covers some positives, F covers some other positives, HG covers positives, E also covers positives, but C cannot cover all, covers all negatives. C covers all negatives. See, something like this, but segment ordering cannot be deducted from this tree model. This is very important. For some cases, segment ordering, that is because of outcomers or noise, so we can't, no, definitely we can't say segment ordering cannot be deducted from this tree model. See, something like this. See, there are blue points like this, and similarly there are some red points. So when such data is there, when such data, it is difficult to separate these, and segmentation would be a difficult task in such cases. Now, for that, what we do now? Now let us see. This is called tree pruning. Tree pruning. When a decision tree is built, many of the branches will reflect anomalies in the training data due to noise or outliers. When a decision tree is built, my dear friends, many of the branches will reflect anomalies in the training data due to noise or outliers. Tree pruning methods are used to overcome the problem of overfitting the data. This anomaly is called overfitting. Overfitting under overfitting. Now, to avoid this overfitting, what we do is tree pruning methods are used. Tree pruning methods are used. So, right. Such methods typically use statistical measures to remove the least reliable branches. Remove branch. Most reliable, least reliable. Most reliable and least reliable. Most means very important. Least means negligible. అలాంటి బ్రాంచెస్ తీసుకొని వాటిని రిమూవ్ చేస్తా పోతే దెన్ దట్ ట్రీ ఈజ్ కాల్డ్ ప్రూనింగ్. అంటే ఏంటి దాని అర్థం? ఇట్ ఆల్సో ఎఫెక్ట్స్ అవర్ డెసిషన్, బట్ ఇన్ హౌ మెనీ కేసెస్? ఒక 1000 కేసెస్లో ఒక్క కేసే రేర్గా వచ్చింది. అది వస్తే మనం ప్రిడిక్ట్ చేయం అంతే. But that only happens once in 1000 cases. So అలాంటివి కనుక్కొని అలాంటివి కనుక రిమూవ్ చేయగలిగితే then that is called pruning అంటారు. Pruned trees tend to be smaller and less complex and thus easier to comprehend. They are usually faster and better at correctly classifying independent test data than unpruned trees. So this is called tree pruning, my dear friends. Tree pruning under, right? Let us see now. Now, how do we ranking ela chestam? The ranking obtained from the empirical probabilities in the leaves of a decision tree yields a convex ROC curve on the training data. We have just seen now. So, adding a split to a decision tree, can be interpreted in terms of coverage curves as the following two-step process. Split the corresponding curve segment into 2 or more segments. Reorder the segment on decreasing slope. So reorder the segment on decreasing slope. This is called slope, my dear friends. Decreasing slope. Reorder them in decreasing slope. So the whole process of growing a decision tree can be understood as an iteration of these two steps. An alternative is a sequence of splitting steps followed by one overall reordering step. It is this last step that guarantees that the coverage curve is convex. So this is how ranking. Now there are some, right, we'll see. See, this is how it is. Right. Now the class distribution in the leaves of an unlabeled feature tree can be used to turn one and the same tree into a decision tree or a ranking tree or a probability estimation tree. A class distribution in the leaves of an unlabeled feature tree can be used to turn into a decision tree, a ranking tree, or a probability estimation tree. Elaga, see, to turn a feature tree into a ranker, we order its leaves on non-increasing empirical probabilities, which is probably optimal on the training set. So we turned into ranker, a tree ranker. To turn the tree into a probability estimator, my dear friends. To turn a feature tree into a ranker, this is, we can turn, this is to a ranker. To turn the tree into a probability estimator, we predict the empirical probabilities in each leaf, applying Laplace's and M-estimate smoothing to make these estimates more robust for small leaves. So we can easily turn the tree into a probability estimator by just we predict the empirical probabilities in each leaf. Probabilities estimate చేస్తావు by applying Laplace smoothing. So ఈ విధంగా చేస్తే it can easily be converted into probability estimator. Similarly, even a decision tree can be turned to tree into classifier. We choose the operating conditions and find the operating point that is optimal under those operating conditions. This is how a feature tree can be converted into a decision tree can be converted into a decision tree, a ranking tree, or a probability estimation tree. So now what do you mean by pruning? The operation of merging all leaves in a subtree. Operation of merging all leaves in a subtree is called pruning the subtree. See, this is how it is. This is all leaves are at one level. All leaves are at one level. See, operation of merging all leaves in a subtree. Merging all leaves in one subtree or in a subtree is called pruning the subtree. So the advantage of pruning is that we can simplify the tree without affecting the chosen operating point, which is sometimes useful if we want to communicate the tree model to somebody else. No, మనం ఎవరికన్నా tree model గురించి చెప్పాలి అనుకున్నప్పుడు this is definitely a better one. But the disadvantage is that we lose ranking performance, my dear friends. Ranking performance. In such case, no, pruning is conditioned pruning. That is, you only when, see, pruning is therefore not recommended unless ఎప్పుడు రికమెండ్ చేస్తారు ఎప్పుడైతే you only intend to use the tree for classification, not for ranking or probability estimation. Ranking, probability estimation ki ganaka vaadakapothe only for classification ki vaadite, then pruning is useful. Otherwise don't use. Or if you define the expected operating condition with sufficient precision, then you can use pruning. One popular algorithm for pruning decision tree is called reduced pruning, my dear friends. Reduced pruning, reduced error pruning, reduced error pruning. Let us discuss this in detail.
Here is that we've got 10 different customers, we've got their genders, we've got their occupation, we've got their age, we've got something like, did they, some target, should we target them for a specific promotion or did they respond for a specific promotion? So this is a target variable that I'm interested in being able to predict accurately. Right? So in different contexts it could mean different things, but I'd like to understand, think of these as red, blues, right, wrong, target, not target, send a promotion, don't send a promotion, will they react, will they not react, whatever you want to call it. However, we'd like to understand, can I use these to better predict these targets? Now, of course, I can't visualize this easily because this is in three-dimensional space, while I can think of these ones and zeros as red or blue points in three-dimensional space. It's going to become harder to visualize in three dimension. So what I'm going to do is I'm just going to draw decision trees. I'm going to start by saying, hey, I'm going to start with the root node and I'm going to try branching either with gender or occupation or age. Now with gender and occupation, there are only two categories, male and female. So the only way I can do is, if I want to try this, I want to start with the root node, and then I have to say, hey, male on the left and female on the right, and come up with two groups. Obviously, the first thing I'm going to ask is, if I do this, what kind of Gini impurity do I have on this as opposed to this? So let's calculate the Gini impurity of the root node to begin with. So let's start with that. So, and hopefully, if this is an improvement, then I will do the branching. If this is not an improvement, I won't do the branching. So let's calculate this. So if you do look at all of that, I've got 1, 2, 3, 4. So for the root node, P1 is 0.4 out of 10, 4 out of 10, and P2 is 0.6. Okay, now let me quickly write down what P1 and P2 are. So I'm going to use P1 to indicate probability of target equal to 1, and P2 as probability of target equals 0. Again, I could have called it P1 and P0, but I'm just calling it this way. In my mind, P1 is probability of category number 1 and P2 is probability of category number 2. So even if your targets were things like gender or whatever, it doesn't have to be zeros or ones. You can still call it P1, P2, P3 and so on. So this is what I will use as notation. So the impurity, if you will, it's closer to 0.5, so you can guess that the impurity is going to be quite high. The impurity, Gini impurity, Gi, let's call it, is equal to 1 minus 0.4 square minus 0.6 square. I'm just using this formula that we just derived earlier. Here we go. So 1 minus summation of all pi squares. That's all I'm using. When I do this, all I'm going to have is this simplifies to something like 0.48. So it's really, really impure. Now what I'm going to do is, if I do split according to this section here and call this group 1 and call this group 2. If I do that, let's call it group 1 and group 2. That looks like, let's call it group 1 and group 2. For group 1, which is male, and group 2, which is female, I can still again calculate the Gini impurities. So if I do look at group 1, what happens in group 1? Let's do group 1 and group 2, and we'll need to combine them together in a minute. So let's look at group 1 and group 2 for now. Group 1 and group 2, what is happening is in group 1, 1, 2, 3, and P1 is equal to 0.5. P2 is also equal to 0.5. So that's going to give me 1 minus 0.5 square minus 0.5 square, and that gives me 0.5. And here it's 0.48. And in the group 2, P1 looks like it's 0.25, and it's a little more purer, particularly because there are a lot more zeros than 0.75, and 1 minus 0.25 square minus 0.75 square ends up giving me a 0.375. Now, of course, I need to combine these two to be able to come up with how much I've gained. So this is how the Gini index I started with, the Gini impurity of Gini index. So Gi I finished with will be a weighted average of 0.5, but there are 6 points. So 6 by 10 of 0.5, it's a weighted average, plus a 4 by 10 of 0.375, giving me all of this, giving me something that is 0.4. How much is this? I thought okay, 0.45. So by splitting from, let's write this down properly. By splitting, I started with 0.48, and by splitting, I got it down to 0.45. That's definitely a gain. That's what people call a Gini gain. So by splitting by male versus female at this top branch here, I did gain a 0.03. However, it's not clear that this is the best split. I need to try splitting by salaried versus self-employed, and I also need to try splitting by age, but when I'm splitting by age, I have to try 22, a split at 22, between 22 and 23, between 23 and 24, between 24 and 25. I'm going to try all of these. That's exactly what a computer will try and do, even for a very large data set. There are efficient ways to do this, but that's literally what the computer ends up doing. So let's try this. This is by male versus female. If we do split by, I'm going to very quickly show you some calculations for what happens if we split by, what is this? Self-employed versus self-employed versus salaried. What happens if we split by that? And we can try this. Of course, we're going to start with a 0.48 again, but that's the same thing. How much does that improve by is the question. If you go back and look at all of these, so I can calculate what happens for salaried. That's 5, 2 out of 5. So for salaried, I can do the same thing. I can calculate 1 is self-employed. I'm going to try and have my calculations here. For salaried, for self-employed, let's do 1 and 2. For this one group here, amongst the self-employed, I'm going to have a Gini index of 1 minus 0.4 square minus 0.6 square, and that will give me something like 0.48. And in 2 also, I'll end up having a Gini index of 1 minus 0.4 square minus 0.6. The proportions are exactly the same. So that's going to give me 0.848. And if I do combine it anyway, Gini index, the combined Gini index of the split, sometimes people call it the Gini of the split and the Gini of the root node. So the Gini index of the split is, again, it depends on, okay, there are 5 out of 10 data points on the first one, that's 0.48. It doesn't really matter. You know that the weighted average is all going to be 0.48 anyway, 48, and that's a 0.48. So by splitting by employee occupation, by splitting by gender at the root node, we get some gain. By splitting by the occupation, we get no gain. Let's try age. With age, things become a little more interesting because age is not a categorical variable. You just don't split by, it's not as simple as splitting by male versus female. What you'll have to end up trying is you've got to try various splits. You've got to try age of less than or equal to 22, comma, greater than 22, less than or equal to 23, comma, greater than 23, and so on. So let's write down less than or equal to 24, greater than 24, less than or equal to 25, and greater than 25. So these are their left and right splits, and I'm not going to do all the calculations for each one. I'm just going to give you the results. So if you do, you can double check these. The left, which is left, and which is right, right. Remember, the combined one is always 0.48. Now, if I do split at 22, then the left turns out to be, the Gini index turns out to be 0.5, and the right was 0.47. The combined one, the Gini split, let's write it as Gini split, which is the combined one turns out to be 0.48, no gain. The second one is 0.5, 0.44, 0.47, a little bit of gain, but still not as good as even your male versus female split. The third one is 0.5 and 0.38, and again 0.45 again, but equal to that of a male versus female split. But the last one, when I split at 25 and 26 and above, what happens is, you can see this here, when I split at this level, all of these are 0.5, 0.5, quite impure, but this section becomes quite pure, and therefore this turns out to be much better comparatively, 0.40, and the gain here is 0.08. The difference between 0.48 and 0.40. And this turns out to be the best split. So your CAR technique is going to come in and say, hey, at the root node, your first split that I suggest is to go with less than or equal to 25 and greater than 25, which is 26 and above, right? That's going to be the best split that increases your gene impurity from 0.48 to a combined 0.40, right? That's the best Gini gain you can gain out of all the possible splits I have tried. That's what the computer is essentially telling us. Now this, once you do this, then this whole process of trying every